So as we look at evaluating this improper integral, we have to kind of acknowledge the fact that the lower and the upper bounds are both finite, and neither of these pose a mathematical problem. If we plug 0 into here, we get a denominator that's not 0. So this is a definable value. And same with 2. If we plug in 2 here, we can also find out the value for that. So we have to recognize that when we talk about this pinching off here, we're talking about this asymptotic behavior, and the real issue then is to as we look at this pinching behavior, we're looking at really what happens at x equals 1. So, and that happens to be right where this asymptote is, right here. And so when we look at this integral, we're looking at, from 0 to 2. So we're looking at this portion of the just this portion of the graph, and we're saying, does that lead to a finite value as this pinching is occurring about this asymptote? And so in order to kind of talk about the improper nature of this integral, we need to split this integral up into 2 separate pieces. And so we have a left-hand side here that is from this left side is from 0 to 1. So this left-hand side here is from 0 to 1 of 1 minus x to the 2/3 power. And then this right-hand side over here is from 1 to 2. Of the integral of 1 over 1 minus x to the 2/3 power. And so now we can see that we have this improper upper bound for this one and this improper lower bound for this one. We also could notice that, and this saves a little bit of time mathematically, is that we have some symmetry here about this asymptote. So this left-hand side is the same symmetrically as this right-hand side. So I'm just going to arbitrarily choose this right-hand side here. And I'm going to find the value of that integral from 1 to 2. And if I get a finite value, then I can always double a finite value. So, and if I get an infinite value, I can't double it. So that should be able to tell me there with half the amount of work. So if we're looking at that right-hand side from 1 to 2, then we can rewrite that and in terms of finding the limit as it approaches that improper limit, which would be that lower limit. So if we look at that, we're talking about the limit as, we'll call it A, approaches 1, and we're approaching 1 from the right-hand side, that's the larger side, from A to 2 of 1 over 1 minus x to the 2/3 power. And so we're looking at evaluating that. So I'm going to kind of step aside here and say, let's just evaluate this limit. I'm going to call that 1 minus x to the negative 2/3, so I can do the power rule here. So we add 1 to this, that gives us a positive 1/3. We take the reciprocal, which is 3 over 1, and times the quantity 1 minus x to the 1/3 power, and then we have to do the chain rule in here to take the get the or u sub, I guess technically, to get that appropriate negative sign out there. So we have negative 3 1 minus x to the 1/3 power is the value of this integral. So really what we're doing is we're taking the limit of that as a approaches 1 from the right-hand side of 3 times 1 minus x to the 1/3, and we're evaluating that from A to 2. And so as we plug in the upper and the lower limits, we're talking about the limit as A approaches 1 from the right of 3 times 1 minus 2 to the 1/3. Oops, I dropped my negative sign there. That was my mistake. Minus a negative 3 times 1 minus A to the 1/3. So as we plug in, as we let A go to 1, this whole thing goes to 0. So this whole term here, negative 3 times 0, drops out to 0. And this is, we can evaluate as negative 3 times negative 1 to the 1/3 power. And so this then is 3, and that's 0. So the area then for half of this, from 1 to 2, is 3. So for the entire expression then, we're talking about from 0 to 2 of 1 over 1 minus x to the 2/3 power dx. As we integrate that, that area approaches the value of 6, which is finite. And so therefore we say that this converges since it reaches a finite value. When asking the same question for this example, does it pinch off fast enough? And this is real similar to the example before it. Again, we have this, this asymptotic behavior. This time it's about the line x equals 2. But we still have this asymptotic behavior. And if I go back to the previous example here, we can see how tight this was about the asymptote. So, so if we look at this, it pinched off really fast. We look at this, it's not pinching off so fast. So if we look at that symmetrical area from x equals 1 to x equals 3. So if we look at this area here, maybe you can start to speculate as to what might happen here in terms of that pinching off. Is it pinching off fast enough, or is your gut telling you that maybe it's not pinching off fast enough? That narrowing here is just not that dramatic like it was in the other example. So we're going to again look at just half of this. So we'll look at the right-hand side again. And so we're going to look at the integral from 2 to 3. And then that's going to make it a little more obvious about the improper nature about this integral. Now we see at this lower bound, it has a undefined, makes this denominator 0, which makes this expression undefined. So we're going to let a approach 2 from the right. I could have used the other side too. And we're going to look at integrating 2 over x minus 2 to the 8/3 power dx. And so again, I'm going to kind of step aside here and just do the integrations. This lower bound would then be a, and this upper bound would be 3. So I'm going to pull out the 2. I'm going to integrate from a to 3. X minus 2 to the negative 8/3 dx. So when I look at this, let's see, bumping this up by 1 is going to make it 8/3 plus negative 8/3 plus 3/3, which is going to make it negative 5/3. And flipping that is going to be negative 3/5. X minus 2 to the 5/3, to the negative 5/3, excuse me. And then looking at a u sub in the middle here, we don't have anything that we need in terms of a constant out here. So we're going to evaluate that from a to 3. And so doing that little bit of math out here, we get negative 6 over 5. X minus 2 to the, in fact, I'm going to write that as a positive exponent. So I'm going to write that as negative 6 over 5, 1 over x minus 2 to the 5/3 from a to 3. And so as we take that limit, as a approaches 2 from the right-hand side of negative 6 over 5 times x minus 2 to the 5/3, get fraction line a little bit bigger, from a to 3, we're looking at negative 6 over 5, 3 minus 2 to the 5/3, and minus a negative 6 over 5, 3 minus a to the 5/3. And if I take that, and I forgot to write the limit in front of it, I guess I really can't move it. Sure I can, hold on, let me just ungroup this. Oops. Now let me just squeeze it in here. See if I can just squeeze the limit as a approaches 2 from the right-hand side. So as we look at this, this is 6 over 5. Minus a negative is a plus, and then we get a 6 over, and I wrote this wrong, this is a minus 2. There we go. So this is x minus 2, so this is a minus 2. There we go. As we put in a 2 here, we get 0 to the 5/3, so that's infinite. And so if the right-hand side is infinite, the left-hand side has to also lead to an infinite value. So if we're looking at from 1 to 3, the integral up here of 2 over x minus 2 to the 8/3 power dx, we're looking at an infinite value for the area, and so since that is infinite, the limit does not exist, then we talk about this being divergent.